The universe is expanding. If you zoom out far enough, the universe looks like it's coming apart at the seams, galaxies racing away from one another as space itself stretches faster and faster. So here's the question that shouldn't make sense. If everything is expanding, why hasn't our corner of the universe fallen apart? The Milky Way isn't alone. It's surrounded by dozens of other galaxies drifting through space in a loose collection called the local group. And according to everything we know about cosmic expansion, they should be slowly pulling away from each other. But they aren't. In fact, many of them are moving too fast to be held together by the gravity of stars and gas alone. And the biggest members, the Milky Way and Andromeda, aren't separating at all. They're on a direct collision course. This creates a paradox at the heart of modern cosmology. The universe is accelerating outward, driven by a mysterious force we call dark energy. Yet right here, on scales of a few million light-years, gravity has won. Something unseen is holding this system together, something massive enough to overpower cosmic expansion and keep these galaxies bound as a single structure. In this episode, we're going to unravel how the local group stays intact, why its galaxies move the way they do, and how invisible forces, dark matter and dark energy, quietly shape the fate of everything we see around us. Before we go further, be sure to like this video and subscribe to the channel. Your support is greatly appreciated. Before we can understand why the local group stays bound, we need to be clear about what it actually is, because this isn't just a casual neighborhood of galaxies drifting near one another. It's a true gravitational system. The local group spans roughly 10 million light-years and contains more than 50 known galaxies, but nearly all of its mass and influence is dominated by two giants, the Milky Way and Andromeda. Around them orbit a swarm of much smaller galaxies, dwarfs that are faint, fragile, and easily distorted by gravity, along with a few irregular galaxies that refuse to settle into clean spiral shapes. These galaxies are not scattered randomly through space. Their positions, motions, and shapes all reveal a shared history, one shaped by gravity acting over billions of years. Many of the dwarf galaxies cluster around the two major spirals, following elongated paths and leaving behind streams of stars that trace their orbits like contrails. The local group itself is embedded in a much larger cosmic web, connected to nearby groups and clusters, yet it remains a distinct structure with its own internal dynamics. What makes this remarkable is the scale. Over millions of light-years, this collection of galaxies behaves less like debris floating in an expanding universe and more like a bound system, one that should not exist if only the matter we can see were responsible for holding it together. When astronomers first measured the motions of galaxies within the local group, they ran into a puzzle. The stars and gas we can see simply don't provide enough gravity to keep everything from flying apart. The Milky Way and Andromeda are moving toward each other far too quickly, and the smaller dwarf galaxies orbit their hosts at speeds that, by the calculations, should send them escaping into intergalactic space. This is known as the binding problem. The visible mass isn't enough to explain the observed motions. To make sense of it, scientists rely on the concept of gravitational binding. A system stays together when its total kinetic energy, the energy of motion, is less than the gravitational potential energy pulling it inward. Observations show that for the local group, the visible matter alone falls short by a huge margin. Without some additional invisible mass, the galaxies would have dispersed billions of years ago. This discrepancy was one of the first hints that something fundamental was missing from our understanding of the universe. A hidden component that doesn't shine, doesn't radiate, and yet exerts a powerful gravitational influence, quietly holding the local group together against the relentless expansion of space. Dark matter is the invisible scaffold that holds the local group together, the hidden substance that makes up the vast majority of the mass in galaxies and galaxy clusters, yet refuses to interact with light in any way we can detect. Unlike stars, gas, or dust, dark matter does not emit, absorb, or reflect light, making it completely invisible to telescopes. It does, however, exert a powerful gravitational pull, shaping the motions of galaxies and the evolution of cosmic structures across billions of years. Within the local group, both the Milky Way and Andromeda are surrounded by massive halos of dark matter, enormous spherical regions that extend far beyond the visible edge of the galaxies themselves. These halos contain far more mass than all the stars combined, and their gravitational influence reaches out to the smaller dwarf galaxies orbiting the larger spirals, guiding their paths and keeping them bound to the group. Without these halos, the local group would not be a cohesive structure. The galaxies would drift apart, pulled away by the expansion of the universe. One of the most compelling ways to see dark matter in action is by observing these smaller, faint galaxies. Dwarf galaxies, which can contain only a few million stars, provide some of the clearest evidence for dark matter because their internal motions reveal far more mass than is visible. In many cases, the stars move so quickly that if only the star's gravity were present, the galaxies would fly apart within a few million years. The only way to explain their survival is to assume that each dwarf is embedded in its own dark matter halo, containing hundreds or even thousands of times more mass than the stars themselves. Take, for example, the Draco dwarf or the Fornax dwarf galaxies. The measured speeds of their stars indicate enormous, unseen mass, confirming that dark matter dominates their structure. Even the Sagittarius dwarf, which is in the process of being torn apart by the Milky Way, shows signs of dark matter being stripped along with stars, leaving a trail that maps the invisible halo's influence. The presence of dark matter halos around all these galaxies not only explains why they remain bound, but also why the local group as a whole holds together against cosmic expansion. The Milky Way and Andromeda, two massive spirals on a collision course, are each embedded in overlapping halos that interact gravitationally, ensuring that their mutual attraction dominates over the push of expanding space at this scale. The smaller satellites orbit within this shared gravitational environment, their paths determined by the combined influence of both the visible and invisible mass. Dark matter also explains larger structural features, such as stellar streams, and the coherent motion of galaxy groups within the local group. When dwarf galaxies pass near the Milky Way or Andromeda, tidal forces can strip stars from their outer regions, forming elongated streams that arc through space. These streams, which can stretch tens of thousands of light years, trace the contours of the dark matter halos, acting as cosmic signposts of the invisible gravitational landscape. Without dark matter, these streams would be chaotic or non-existent, because the gravitational pull required to shape them simply would not exist. Observations of these structures give astronomers a way to map dark matter indirectly, revealing its distribution, density, and shape. Beyond the local group, dark matter is a critical component in the formation of galaxies and clusters across the universe. Simulations of cosmic structure that exclude dark matter fail to reproduce the distribution of galaxies we observe today. With it, however, the intricate web of filaments, clusters, and voids emerges naturally. Dark matter serves as the framework on which visible matter accumulates, guiding the growth of stars, galaxies, and larger systems over billions of years. Yet despite its central role, the fundamental nature of dark matter remains one of the greatest mysteries in physics. We know it exists because of its gravitational effects, But whether it is made of weakly interacting massive particles, primordial black holes, or some entirely unknown form of matter is still an open question. Studying the local group, with its rich variety of galaxies, provides a unique laboratory for understanding dark matter in detail. By observing how galaxies move, interact, and evolve in this nearby environment, astronomers can test theories about the properties of dark matter and its role in shaping cosmic structures. In essence, dark matter is the invisible hand that orchestrates the motion of galaxies within the local group, the hidden glue that binds this small island of the universe together, and a key to understanding the unseen majority of matter that governs the cosmos. The smallest galaxies in the local group, the dwarf galaxies, provide some of the clearest evidence for dark matter, acting like cosmic laboratories where its presence is impossible to ignore. These galaxies are faint, containing only a tiny fraction of the stars found in the Milky Way. Yet the stars they do have move at speeds far too high to be held in place by visible matter alone. Observations reveal mass-to-light ratios that are staggering, sometimes hundreds or even thousands of times greater than what the stars alone can account for. Some dwarfs, like the Draco and Fornax galaxies, show stars tracing elongated orbits, while others, such as the Sagittarius dwarf, are being stretched and torn apart by tidal forces, leaving behind stellar streams that trace the invisible contours of their dark matter halos. These motions tell a story. The gravitational pull keeping these galaxies intact is dominated not by the stars we can see, but by dark matter lurking unseen. Without it, these fragile systems would simply disperse, their stars scattered across intergalactic space. By studying dwarf galaxies, astronomers can map the shape and extent of dark matter halos, revealing the hidden architecture that governs the dynamics of the entire local group. The motions of galaxies within the local group reveal a dynamic, ever-shifting system shaped not just by visible matter, but by the invisible scaffolding of dark matter. To understand this, it helps to imagine the local group not as a static collection of galaxies frozen in place, but as a living, breathing system where every galaxy is in motion, responding to the gravitational pull of its neighbors. At the heart of this motion are the two giants, the Milky Way and Andromeda. These two massive spirals dominate the gravitational landscape of the group, and their interaction has been shaping the orbits of surrounding galaxies for billions of years. The Milky Way, with its halo of dark matter extending well beyond the visible disk, exerts a gravitational pull that keeps dozens of smaller dwarf galaxies in orbit, many of which move in highly elliptical paths that bring them close to our galaxy before swinging them far out again. Andromeda, slightly more massive, mirrors this behavior, capturing its own retinue of satellites and shaping their trajectories. Observations of these motions are essential because they allow astronomers to trace the total mass of the system, visible and invisible, and to map the structure of the dark matter halos that dominate the local group. One of the most striking examples of motion within the local group is the approach of Andromeda toward the Milky Way. The two galaxies are moving toward each other at roughly 110 kilometers per second, a speed far too great to be explained by the pull of visible matter alone. This collision course is a cosmic inevitability dictated by gravity. In a few billion years, the two galaxies will merge in a spectacular event that will reshape the central region of the local group. But long before that collision occurs, the motions of Andromeda and the Milky Way already influence the smaller galaxies around them. Dwarf galaxies caught in the gravitational tug-of-war between the two giants experience complex orbital patterns, sometimes oscillating between the two, or being perturbed into tidal streams as their outer stars are stripped by gravitational forces. These tidal streams are more than just cosmic debris. They serve as visible traces of the underlying dark matter structure, mapping out the contours of halos that cannot be seen directly. By carefully measuring the velocities and paths of these galaxies, astronomers can infer the mass and shape of the dark matter that governs the local group's dynamics, revealing an unseen web that holds the system together. Beyond the immediate influence of the Milky Way and Andromeda, the local group exhibits motions that are a result of both local gravitational interactions and the larger cosmic environment. The galaxies within the group are not isolated. They exist in a vast network of cosmic filaments and voids that extend across millions of light years. While the local group is gravitationally bound, meaning its galaxies are held together despite the universe's expansion, its motion relative to other nearby groups and clusters introduces additional complexity. The local group itself is moving at roughly 627 kilometers per second, relative to the cosmic microwave background, pulled by the combined gravitational influence of neighboring structures such as the Virgo cluster and the Great Attractor. These external motions are subtle compared to the internal dynamics of the group, but they provide context, showing that the local group is part of a larger interconnected cosmic web, where gravity governs the motion of matter on scales ranging from dwarf galaxies to superclusters. The smaller dwarf galaxies are particularly valuable for understanding motion because their orbits respond sensitively to the mass distribution of the giant's dark matter halos. Some dwarfs follow relatively stable circular paths, suggesting they are deep within the gravitational well of their host galaxy. Others, especially those on elongated orbits, experience tidal forces that gradually strip stars from their outer regions. These stripped stars form streams that wrap around the host galaxy like ribbons, providing a fossil record of past interactions. By studying these streams, astronomers can not only measure the mass of the dark matter halo, but also detect asymmetries or irregularities in its distribution, revealing that dark matter is not always smooth, but can have clumps and variations that influence the motion of satellites. In some cases, interactions between dwarf galaxies themselves can further complicate orbits as they exchange energy and angular momentum, leading to chaotic trajectories that can only be understood by considering the combined gravitational influence of multiple bodies. The timing argument is another powerful tool for understanding motion within the local group. By analyzing the relative positions and velocities of the Milky Way and Andromeda, astronomers can estimate the total mass of the system required to produce the observed approach. This method, applied to other pairs of galaxies and to the local group as a whole, consistently reveals a discrepancy between the visible mass and the total gravitational mass, providing additional evidence for dark matter. In essence, the motions of galaxies act as a natural scale. The faster they move, the more mass must exist to keep them bound. Without the unseen mass of dark matter, the local group's current configuration would be impossible. The galaxies would have already flown apart under the influence of their own velocities and the expansion of the universe. Finally, the motions of galaxies within the local group highlight a delicate balance between gravity and cosmic expansion. On small scales, gravity dominates, holding the group together and orchestrating intricate orbital patterns. On larger scales, however, the expansion of the universe driven by dark energy gradually pulls galaxies apart, stretching space itself. The local group represents a rare and stable pocket where gravity is one, allowing galaxies to interact, merge, and evolve over billions of years. By observing these motions, we not only map the invisible architecture of dark matter, but also gain insight into the forces shaping the universe at every scale, from the paths of individual stars to the grand dance of galaxies. The local group in motion becomes a living laboratory where we can see the invisible at work. a dynamic system that tells a story of unseen matter, gravitational influence, and the cosmic forces that govern everything we observe. Even though the local group is a gravitationally bound system, it exists within a universe that is expanding at an ever-accelerating rate. This creates a fascinating contrast. On small scales, gravity dominates and keeps galaxies tightly bound. But on larger scales, the expansion of space driven by dark energy is relentless, pushing distant galaxies away from each other at ever-increasing speeds. To understand why the local group does not simply drift apart along with the rest of the universe, it's important to grasp what cosmic expansion really means. The expansion isn't galaxies moving through space like cars on a highway. It is space itself stretching, carrying galaxies along like raisins embedded in rising bread dough. Over vast distances, this expansion dominates, separating clusters and superclusters of galaxies. Yet, within regions where gravity is strong enough, like the local group, expansion is essentially irrelevant. Gravity overcomes the stretching of space, keeping the galaxies bound and orchestrating their intricate dance. The concept of dark energy, discovered in the late 1990s through observations of distant supernovae, adds another layer to this cosmic picture. Dark energy is a mysterious force that permeates all of space, accelerating the expansion of the universe. Its effects become more pronounced over vast distances, influencing the motion of clusters of galaxies billions of light years away. Within the local group, however, the gravitational pull of the Milky Way, Andromeda, and their satellite galaxies is far stronger than the repulsive push of dark energy. This is why, despite the universe expanding everywhere else, the local group remains a coherent, bound system. The contrast is striking. Galaxies just beyond the local group are being carried away by cosmic expansion, while the galaxies inside remain tightly knit, a gravitational island in an ocean of stretching space. The interplay between local gravity and cosmic expansion can be visualized as a cosmic tug-of-war. On one side, gravity pulls galaxies toward each other, binding them into a cohesive system. On the other, dark energy stretches the fabric of space, pushing everything apart. The local group is a case where gravity has decisively won on small scales. All the galaxies within roughly a few million light-years of the Milky Way and Andromeda are moving under the influence of mutual gravitational attraction, ignoring the push of dark energy. This balance is why the Milky Way and Andromeda are on a collision course, why dwarf galaxies orbit their hosts in complex paths, and why the group's overall structure remains intact despite the universe expanding around it. Understanding this balance is critical because it illustrates a fundamental principle of cosmology. While dark energy controls the fate of the universe on the largest scales, gravity dominates on small, bound systems, shaping their evolution in ways we can directly observe. Interestingly, the boundary between gravitationally bound systems and expanding regions is not sharply defined. Galaxies at the outskirts of the local group may feel both the pull of the group's combined gravity and the push of cosmic expansion. Some dwarf galaxies, for example, are on the edge of the group's gravitational influence. Their velocities are such that they may eventually escape if they receive an extra gravitational nudge, or they might remain bound for billions of years, depending on the mass distribution within the group. These transitional galaxies serve as natural laboratories for studying the limits of gravitational binding and the influence of dark energy at intermediate scales. By observing their motions, astronomers can measure how gravity competes with cosmic expansion, providing clues about both the unseen dark matter that holds the group together and the dark energy that accelerates the universe on large scales. On even larger scales, the local group's relative isolation makes its dynamics more apparent. The nearest massive neighbor is the Virgo cluster, roughly 50 million light-years away, which exerts a gravitational influence on the local group as a whole. Beyond Virgo, the expansion of the universe dominates, carrying other galaxy clusters away at accelerating speeds. This hierarchical structure highlights an important principle. Gravitational binding is a scale-dependent phenomenon. The local group is strongly bound. The Virgo cluster is bound on a larger scale, and superclusters beyond that are only partially bound, with expansion increasingly dominant. This creates a nested cosmic structure where gravity wins locally but loses on the largest scales, a pattern repeated throughout the observable universe. Dark energy also influences the long-term fate of the local group. While the group itself is secure, isolated and bound, the rest of the universe is not. Over the next tens of billions of years, galaxies outside the local group will recede so rapidly that they will disappear from view, leaving the local group as a solitary island in a vast, dark expanse. This makes the study of local dynamics even more significant, because the local group may become the only directly observable cosmic structure in the distant future. For astronomers billions of years from now, all evidence of the broader universe may be gone, and the motions of Milky Way, Andromeda, and their satellites will be the only clues to the forces that shape the cosmos. In practical terms, the competition between gravity and cosmic expansion also explains why the local group has survived for billions of years without disruption. Gravity ensures that internal interactions, mergers, tidal stripping, and orbital motion proceed according to predictable patterns. Meanwhile, the push of dark energy is negligible on these scales, allowing galaxies to interact over cosmic time without being torn apart by the stretching of space. Observations of galaxy motions, stellar streams, and the approaching collision between the Milky Way and Andromeda confirm that the local group is dynamically evolving under gravity's control. The group is effectively a gravitational bubble, immune to cosmic expansion within its boundaries, providing a controlled environment where astronomers can study galaxy dynamics, dark matter distribution, and the long-term effects of gravitational interactions. Ultimately, the local group illustrates a profound cosmological lesson. The universe behaves differently depending on scale. On vast scales, dark energy dominates, accelerating expansion and shaping the large-scale structure of the cosmos. On smaller scales, like that of the local group, gravity reigns supreme, keeping galaxies bound and orchestrating their motions. This interplay allows astronomers to study dark matter and galaxy evolution in a relatively stable environment, while simultaneously observing the influence of dark energy in the universe at large. By examining the local group in motion, we see the delicate balance between opposing cosmic forces, a balance that governs the fate of galaxies, both near and far, and that will determine the ultimate isolation of our galactic neighborhood in the distant future. The study of the local group offers far more than just a glimpse at the motions of nearby galaxies. It provides a window into the fundamental forces that shape the universe itself. By observing how galaxies interact, orbit, and sometimes collide, astronomers can trace the influence of dark matter, the invisible substance that dominates the mass of galaxies, as well as understand how cosmic expansion, driven by dark energy, sets the broader stage for their evolution. The local group is, in many ways, a natural laboratory for cosmology. It is close enough that we can measure the motions of individual stars and satellite galaxies, yet it is large enough to reflect the complex interplay between gravity and expansion that governs the universe on a larger scale. Every galaxy within the group, from the largest spirals to the faintest dwarfs, carries clues about the underlying distribution of mass, both visible and invisible, and these clues are encoded in their paths through space, the streams of stars torn from satellites, and the interactions between neighboring galaxies. One of the most striking lessons the local group teaches us is the importance of dark matter. Observations consistently show that visible matter alone cannot account for the motions we see. Stars in dwarf galaxies move too fast to be held in place by the gravity of the few stars they contain. And the velocities of the Milky Way and Andromeda require far more mass than what is visible in stars and gas. Dark matter provides the missing piece, forming massive halos around galaxies that dominate their gravitational potential and guide the motions of satellites. By studying the local group, astronomers can map these halos with unprecedented precision. Stellar streams and tidal debris act as tracers, revealing the shape, extent, and sometimes even the clumpiness of dark matter. The dwarf galaxies themselves, often dominated almost entirely by dark matter, serve as natural experiments, showing how this invisible substance governs dynamics even when only a handful of stars are present. These insights are crucial, not just for understanding the local group, but for testing the broader predictions of cosmology and particle physics. At the same time, the local group demonstrates the scale-dependent effects of cosmic expansion. Dark energy is the force driving the accelerated expansion of the universe. Yet its effects are negligible within the local group. Here, gravity wins, and the galaxies remain bound, interacting over billions of years. This contrast between local gravitational dominance and large-scale expansion allows scientists to study both forces in a single system. They can observe the stability and internal dynamics of a gravitationally bound group, while also understanding how such systems fit into a universe that is steadily stretching apart. The local group thus acts as a bridge between two regimes of cosmic behavior, showing how the same fundamental laws of physics manifest differently depending on scale. Beyond the scientific insights, the local group provides a cosmic perspective that is both humbling and profound. The galaxies we observe today have been interacting for billions of years, shaped by forces we cannot directly see, yet whose effects are written across the sky. In the distant future, the local group may become even more isolated as expansion carries other galaxies beyond the reach of observation. For future astronomers, the Milky Way, Andromeda, and their satellites may be the only visible galaxies in the universe, serving as the sole record of cosmic history. Studying the local group now allows us to understand not only the present state of our galactic neighborhood, but also the forces that will determine its ultimate fate. In essence, the local group is a microcosm of the universe, a bound system where gravity, dark matter, and cosmic expansion interplay in ways that reveal the hidden structure of the cosmos. It teaches us that the universe is not uniform on all scales. Regions like our own can resist expansion and evolve through collisions, mergers, and orbital interactions, while more distant regions are carried apart by dark energy. By examining the motions, interactions, and composition of local group galaxies, astronomers gain insight into the fundamental forces that govern all matter, the unseen architecture that holds galaxies together, and the eventual isolation of our cosmic neighborhood. Studying the local group is not just about mapping nearby galaxies. It is about understanding the universal principles that shape the cosmos, giving us a glimpse of the invisible threads that bind everything together. As we reach the conclusion of our journey through the local group, it becomes clear that this collection of galaxies is far more than a simple neighborhood in space. It is a living, dynamic system shaped by forces we cannot see. Gravity binds the Milky Way, Andromeda, and their satellites together, orchestrating complex orbits, tidal interactions, and even future collisions, while dark matter provides the invisible mass that holds it all in place. Meanwhile, the universe around us continues to expand, accelerated by dark energy, stretching galaxies beyond our reach and highlighting the delicate balance between local cohesion and cosmic dispersal. Thank you for watching. If you enjoyed this video, be sure to like and subscribe for more content like this, and tell us what is your favorite fact about the local group. Take care and never stop exploring.